Their job is fairly simple: mix the fuel into the air and ignite it. A simple job that started development in 1995 with both General Electric and NASA. The art of crafting the perfect fuel injection nozzle is incredibly complex, a delicate yet violent process, like an orchestra whose crescendo is a fiery explosion. With the advent of 3D printed manufacturing, GE has been able to create a fuel injector with a complex internal labyrinth of air channels that traditional tooling simply could not cut. The fuel injector they developed is called the Twin Annular Pre-Swirl Injector, or TAPS. So how does it avoid those dangerous nitrous oxide emissions? By carefully controlling the air-fuel mixture ratios to control flame temperatures. If we plot flame temperatures against air-fuel ratio, we get something that looks like this: the max flame temperatures occurring at stoichiometric air-fuel mixtures. That is, the mixture where air and fuel are both entirely consumed in the reaction. This is the zone where nitrous oxide emissions are highest because the flame temperature is highest. To minimize nitrous oxide emissions, we can aim to be over on this side of the curve with a rich air-fuel mixture. But that would result in a lot of wasted unburnt fuel. So instead, we aim to be over here on the lean side of the graph. If we map the combustion process for GE's previous injector fitted to over 22,000 CFM56 engines, we would see the air-fuel mixture is initially injected in this zone with a rich air-fuel mixture. Then it goes through a dilution process to reach a lean mixture where the fuel is fully consumed. The issue with this is that the fuel goes through the stoichiometric region in between these two phases, creating a great deal of nitrous oxides. The TAPS fuel injector looks like this, with a central main pilot surrounded by a ring-shaped main injector, creating two swirling airflows that look something like this, which uses a large amount of air in the pre-mixing phase to ensure thorough mixing and a lean air-fuel mixture. If we map the combustion process of TAPS, it starts in the lean zone and gets even leaner further into the combustor, never getting close to the peak nitrous oxide production region. This may seem like a simple device, but it took generations of design iterations with computer simulations gradually bringing the engineers closer to their target. And none of their designs would have been possible without current generation metallic 3D printing that could manufacture the complex parts with the materials capable of resisting the enormous heat within the combustor. 26 years of development paid off with 60% nitrous oxide emission reductions, a fuel injector compatible with the record-breaking 58:1 pressure ratio used in the GE NX. GE managed to increase the pressure ratio even though they reduced the number of compressor stages. Each of these turbine discs is one stage. The GE NX contains 10 stages, 4 fewer than the CF6 engine it is replacing. GE managed to do this through new improved blade design, which is a lot less info than I wanted to share, but finding information on this topic was incredibly difficult, a testament to how advanced and secretive the technology is. The compressor does include 3 Blisk stages, which are perhaps the most impressive feats of machining I have ever seen. Traditionally, compressor stages are made by attaching the blades to a separate disc with dovetail connections. This decreases manufacturing complexity, but the dovetail connection is less durable, increases assembly and maintenance costs, and allows some air to escape through the connections. Blisks are compressor stages that are manufactured from a single piece of metal, making them stronger and easier to install, while improving aerodynamic efficiency. Improving aerodynamic efficiency was the name of the game to improve compression ratios, and of course, that needed to apply to the turbine section that powers the compressor. It too benefited from cutting-edge aerodynamic modeling. The turbine also made use of new material science breakthroughs, being the first commercial engine to make use of gamma titanium aluminide, an advanced alloy of titanium and aluminium that combines the heat resistance of titanium with aluminium's weight savings, replacing the nickel alloys of past. It took 3 decades to take this material from the lab to commercial use, and the Dreamliner was the first plane to make use of it, paving the way for the material's acceptance in the industry. All of these factors combined to allow the GE NX engines of the Dreamliner to reduce fuel consumption by 15% over previous generation engines. That is an astronomical leap, and on top of all that, the engine is 60% quieter than similar sized planes, in part thanks to the engine's most distinctive feature, this sawtooth pattern on the fan casing and the engine exhaust. These features are called engine chevrons, and they aren't just futuristic cosmetic design, but functional parts of the engine that significantly reduce engine noise. The question is, what difference can a mere shape change at a nozzle exit have on the overall noise pollution produced by the aircraft? Because turbofan engines force air out of their bypass chambers and turbines at speeds that are much higher than the speed of the ambient air, the air interacts with the free stream air, causing mixing. This mixing causes uncontrolled vortices, which in turn generate excessive noise for both the passengers and the community on the ground. Think of it like water accelerating down a waterfall and striking the water below. That turbulence can be extremely loud. The chevrons aim to control the vortices that are shed from the engine nozzle by creating smaller vortices at each of the teeth of the chevron to allow the hot, fast air being expelled from the engine to mix with the ambient air more gently. This is said to reduce jet blast noise by as much as 30% and allowed Boeing to use substantially less sound insulation in the fuselage walls of the aircraft, which helped to reduce aircraft weight. The 787 truly does live up to its name. It provides a passenger experience that is almost incomparable to that of other commercial aircraft, with advances in noise reduction, fuel efficiency, and passenger comfort. This series is usually saved for aircraft and technology most of us will never set foot in. But the 787 could be the most advanced piece of engineering we have ever covered, and it's a plane many of us will have the opportunity to fly in and marvel at the decades of engineering advancements that made it possible. This nearly half-hour-long video is just half the story, but the full hour-long director's cut version has been available on Nebula for over a week. It combines the two halves of this video released on YouTube into one seamless, ad-free experience that you can sit back and relax to watch. I removed one section from this video detailing the complicated thermodynamics explanation of why compression ratios actually increase efficiency, because it felt just too academic for YouTube. But I think die-hard fans of this channel may enjoy listening to a 10-minute explanation of temperature entropy diagrams. The director's cut also includes explanations of the 787's nifty electronic heads-up display in the cockpit and electrochromic window shades. I felt neither of these topics really fit in anywhere in the larger script. Nebula is the best way to experience our videos. No ads, no distractions, and director's cuts of videos when possible, along with exclusive access to our World War II series, The Logistics of D-Day, and our upcoming Battle of Britain series. If you want to see more content like this, the best way to support the channel is by signing up to Nebula with the Curiosity Stream bundle. I've included a link to the director's cut in the description for those of you already subscribed to Nebula, or if you've yet to start supporting the channel there, you can sign up through the Nebula and Curiosity Stream bundle deal for just $14.79 a year. That's over $1 a month, but that $1 has a gigantic impact on this channel, because we get to own and run our own streaming platform, and that gives us the freedom to create what we want, how we want. A little over $1 a month. This is by far the best way to support this channel and get something in return, with access to both Nebula and all the amazing award-winning documentaries on Curiosity Stream, like this one called Hack the Moon, about the fascinating technologies engineers developed for the Apollo moon mission. You can sign up to this amazing deal by clicking on this button on screen right now. Or, if you are looking for something else to watch right now, you could watch our last video on how vapor cones form on planes, or you could watch Real Science's latest video on how bee communication is helping us learn about the human brain. Little over $1 a month. This is by far the best way to support this channel and get something in return, with access to both Nebula and all the amazing award-winning documentaries on CuriosityStream, like this one called Hack the Moon, about the fascinating technologies engineers developed for the Apollo moon mission. You can sign up to this amazing deal by clicking on this button on screen right now. Or, if you are looking for something else to watch right now, you could watch our last video on how vapor cones form on planes, or you could watch Real Science's latest video on how bee communication is helping us learn about the human brain.